Welcome to this module, and in this module we will understand what exactly the photoresist is. In last module we have seen how we can use a wafer and what are the steps to perform the photolithography, right. We have seen that we can take a wafer, then you have to clean the wafer. After cleaning the wafer, you have to perform several steps to finally obtain the pattern of the photoresist. What are those steps? If you recall, the first step is after wafer cleaning, you have to dehydrate the wafer. That means you have to pre-bake the wafer, and then you have to do primer coating. Primer was HMDS, right. Then next step is you have to spin coat the photoresist. After spin coating photoresist, what is the next step? Soft bake. Soft bake is 90° 1 minute on hot plate. Next step is take a mask, do the alignment, do the exposure. Next step is you have to develop the wafer. Next step is develop the wafer with photoresist developer, that means you are developing the photoresist, right. Next step is you have to do hard bake at 120° 1 minute. Finally, you have to inspect the wafer, inspect the pattern of photoresist on the wafer. That much we have seen. Let us see in this class what are the photoresists. What are the photoresists? Okay. So, if you come on the screen, you can see what are photoresist. So, photoresist is nothing but a polymer, and it is a solid organic material. It is nothing but a solid organic material. The advantage of this is it can be used to transfer the design pattern to the wafer surface. We will see an example. Okay. So, you understand how it is used. Finally, it changes photosolubility due to photochemical reaction exposed to UV light. It changes the photosolubility. That means, we have seen that if I have pattern which is Z, right, I use positive photoresist, then on the wafer this area will be protected. That means, the area of which is not exposed, is protected in case of photoresist, right. If I use Z and if I use negative photoresist, then I will not then I will have everything except this area which is Z. So, let me draw like this. So, it is easier for us to understand. Everything except this area, which is exposed will be strong, and the area which is not exposed will be weak. The area which is not exposed will get weak. You can see here, you can very clearly see what we are getting. It is absolutely opposite of the positive photoresist, right. You see here what we are getting, right. So, in this case we got this, you see. In this case, the area which was exposed, right, the photoresist got etched. That means that if I have this as a mask, this as a mask, and I have a wafer, and I have a square wafer, let us say like this, coated with photoresist. If I have a square wafer coated with photoresist, then if I use positive photoresist and if I used bright field mask, then what I will obtain? I will obtain the pattern which is on the mask, So, what I have done here? I have coated my wafer with a positive photoresist. This is my wafer, silicon wafer or oxidized silicon wafer right, on which there is a photoresist, correct. Now, this is my substrate. If I use positive photoresist, then if I have mask which looks like this, which is Z, right, then I will retain the similar pattern. If I use a mask with a negative photoresist, then the opposite of that of the mask we will get it. That means, here if in another terms the area which is not exposed, you see the area under Z is not exposed, that unexposed area gets stronger. In this case negative photoresist, the area which is not exposed, this area under Z, the area which is not exposed gets weaker. That is why you can see that photoresist from the area which was not exposed is etched, is removed. Here you can see that the photoresist under the area which was not exposed is become stronger. Photoresist under the area which is not exposed gets stronger. In this case, photoresist, which is the negative photoresist case, the photoresist which was not exposed, that area gets it becomes weaker, right. So, this is the example of your positive and negative photoresist. This is example of your positive and negative photoresist. Now, how this happens? Because it changes the photo solubility due to photochemical reaction under the exposure of UV light, because this is photosensitive. That is why it is called photoresist. Okay. Now, I have shown you by showing an example how you can use a photoresist, and if I have a bright field mask, what will happen? Correct. Okay, good. Let us go to the next step. So, next step is, after this we can, what we should do? We should so how we can coat this photoresist, that is a question. Okay. How we can coat the photoresist. So, you guys understood this particular thing, right. So, I am removing it so that you can see what is written. I am removing this schematic. Okay. Now, you can see. So, now the photoresist should have high H resistance and good adhesion, that is a property of photoresist. Okay. So, wafer is held onto the vacuum chuck. So, that means there is a vacuum chuck which is connected, right, to the vacuum pump, and here the wafer is holded on this vacuum chuck. This is our wafer, all right. It is holded on the vacuum chuck. This vacuum is created by connecting this to a vacuum pump, all right. So, then we have to dispense the photoresist, we have to coat the photoresist, we have to dispense it, all right, using a dropper. We can dispense it, right. Dropper is something like this, like a funnel, and you can take the photoresist and you can dispense the photoresist onto this wafer, okay. So, how much? About 3 to 5 ml. Then initially, to have a uniform coating, we will start with a slow spin of 500 rpm. rpm is rotations per minute. Then we ramp it up to 1000 to 5000 rpm, 1100 to 5000 rpm, right. Photoresist is spin coated by a centrifugal force, and the quality measure is time. If I increase the time, my thickness will decrease. If I increase the speed, my thickness will decrease. How uniform the photoresist is, that is another thing. Whether there are particles or defects, that is another thing. So, I have to see lot of things when I am coating photoresist. What is the thickness desired? If my thickness is higher, right, then I have to spin coat it at lower rpm. If my thickness is lower, then I can spin coat it at higher rpm. Then if I have a uniform rpm, if I increase the time, my thickness will decrease. If I decrease the time, my thickness will increase. Whether the PR is uniformly coated or not, whether there are particles and defects or not, everything we have to take care when we use the photoresist, okay. So, it is very important step, extremely important step, and we will see how we can use it. Now, there are several kind of negative photoresist. We have talked about SU8 and then there is ARN 4200, 4300, 4400, positive photoresist from a company Sifley, and also there is AZ3312. So, there are several kind of photoresist, right. Now, this is the same thing that we have discussed, that there are two types of photoresist, one is positive, one is negative. If this is the mask, if this is the mask here which is shown, for the positive photoresist we will retain the pattern. In negative photoresist, opposite of whatever this thing is there will happen. That means, if you consider that this is a mask and the whole wafer was coated with photoresist, then only this area was protected, that means only this area has photoresist. In this case, everywhere there is photoresist except this area, except this area, you see, absolutely opposite of each other, that is why it is positive, that is why this is negative, positive and negative. Alright, excellent, easy, super easy. So, let us see what is the advantage of doing soft baking. Alright, soft baking helps for partial evaporation. Partial evaporation of what? Photoresist solvents, partial evaporation of photoresist solvents. Then second thing is, it will improve the adhesion, improve the adhesion. That means that once you coat on the wafer the photoresist, right, you have to perform soft baking, right, you have to perform soft baking. This is done at 90 degree centigrade for 1 minute on a hot plate, right. So, that you can do, and then this advantage of soft baking is, so that the photoresist, or there is a partial evaporation of solvent, photoresist solvents will get evaporated. Second is, it will improve the adhesion. Third, it will improve the uniformity. Fourth, it will improve the etch resistance. Fifth, it will improve or optimize the light absorbance. Finally, characteristics of our photoresist can be well defined when we do the soft baking. Alright, 6 points we have to remember. Let us see once again. First is partial evaporation of the photoresist solvents. Second is improvement of adhesion. Third is improving uniformity. Fourth is improve etch resistance. Fifth is optimize light absorption. Sixth is characteristics of photoresist is retained, right. That is why we use soft baking. Alright guys. Now comes another topic, which is mask, and we have seen already mask. There are two types of mask, right. We have seen, one is called bright field mask, another one is called dark field mask, right. So, these are master patterns which are transferred to the wafers, right. Whatever there is on the mask, we can transfer it onto the wafer. That is why these are called master patterns, right. Types, how many types of mask? There are two types basically. One is Fe2O3 on soda lime, second one is chrome mask. Okay. Now, based on the field, there is a bright field mask, and there is a dark field mask. So, the pattern here, the mask here that you are looking at is a bright field mask, right. You see, here the field is bright, here the field is bright, here the field is bright, everywhere the field is bright except the pattern, area, right, that is why it is bright field mask. So, for now let us understand what we have seen. We have seen that we can perform the photolithography using photoresist, and then we have seen the type of photoresist, then we have seen how can we see or inspect the wafer, then we have seen why soft baking can be helpful and how it is helpful, and finally we have seen what are the photo mask. Now, I have shown you the photo mask, bright field mask how it looks like, dark field mask how it looks like. So, I am not going to repeat the same thing again and again, because it will get boring, right. So, many things if we have already discussed, if you go on repeating it becomes boring. So, I will not discuss this thing, but we have seen already what are the bright field mask, what are the dark field mask. Okay. So, now until here it should be clear to you that whenever you have a wafer, you have to have a photoresist if you want to do if you want to do a photolithography, if you want to pattern any schematic or any design, right, you need to have a photoresist, right. So, if you have oxidized silicon substrate coated with some material, if you want to pattern it, you need a photoresist, you need a mask, you need a UV exposure. Three things are absolutely clear, right. How can we use the photoresist? I have shown it to you. What kind of mask are there? I have shown it to you, right. And now we will take an example one more time, a different example, and we will see how can you do a complete process of photolithography, alright, using a metal. Then we will move to our favorite thing, which is our MOSFET, and let us see whether you guys can understand the fabrication of the MOSFET, alright. So, till then you guys again read whatever I have taught in this particular class. You understand how we can use photoresist, what are the types of photoresist, what are the types of mask, and how we can use it. What if I use positive photoresist with bright field, what will happen? If I use positive photoresist with dark field, what will happen? If I use negative photoresist with bright field, what will happen? If I use negative photoresist with dark field, what will happen? So, and what is pre baking, what is soft baking, what is hard baking, right? We have seen this. So, let us continue our discussion in the next class. Till then, you take care, have fun, bye.